can get started now. Hello, everyone, and thank you for attending tonight's workshop, An Introduction to Generalized Structural Component Analysis, Structural Equation Modeling, and its applications using free software. As a reminder for tonight, please keep your device muted and your camera off during the presentation unless you have a question. Please type your questions in the chat and the speaker will answer them when we reach a break in the workshop. Without further ado, please allow me to introduce our instructor. Dr. Hyosung Hwang is a professor of psychology at McGill College in Montreal, Quebec, Canada. His research is generally devoted to the development and application of quantitative methods to address diverse issues in psychology and various other fields. Notable recent projects include the development of data integration tools for high-dimensional data collected from multiple sources, the development of statistical methodology for investigating associations among genetic, brain, and behavioral cognitive phenotypes, and the development and application of predictive models or machine learning algorithms for predicting behavioral and cognitive outcomes using genetic, physiological, and psychological data. Thank you for joining us tonight.
Okay, thank you. So let me get started. So first, let me share the, can I share my screen?
Try again.
Okay. Okay, again, thanks for the introduction, Austin, and also thank you everyone for joining this workshop. So let's get started. To start, first actually look at this conceptual model, where we have three different constructs or concepts. So specifically, now we have work stress and SES, social economic status. So these two concepts are supposed to influence another concept or another construct, job satisfaction. So it's more like a multiple linear type model. And of course, we can consider a bit more complex model than this one. Say, we put path, say, from SES to work stress. And by adding this path or the arrow in this picture, simply you're going to test now the indirect effect of SES on job satisfaction through work stress. Or we can also consider one more concept, such as resilience. And by adding this path here, because we try to conceptualize the possible interaction effects between work stress and resilience on job satisfaction. In other words, we may want to test whether the effect of work stress on job satisfaction may depend on resilience and so forth. So anyway, we have all these kind of relationships among four different constructs or concepts, but still this is at conceptual level. This is something we maybe start with when actually when we studying a research project. But as I said, the construct is simply abstract concept, which means it is not directly measurable, just in all sort of our conceptual consideration. This is why in statistical modeling or statistical analysis, we need to represent each construct by some entity directly linked to the empirical data, also called observed variables or indicators. And this kind of process is called a statistical representation of a construct. We'll see some more examples later on about these statistical representations. But by doing so, we can now test various hypotheses among different constructs now statistically. In many cases, simply you replace a single concept with only one measure. That's possible, but in multivariate modeling, there are two actually very well-known statistical representations of constructs. So here, say up to here, this is more at conceptual level. So now you have a construct or abstract concept, such as say work stress or resilience. And then because we want to represent this concept with so-called common factor or simply a factor or a component. Sorry? Do you have a question or everything's okay? Okay. So now this is a statistical kind of level. So here, so we want again, say as an example, one construct such as resilience by either a factor or component statistically. A component is simply a weighted sum of indicators, as I will explain more later on. And again, this is all at statistical level because factors or components are directly linked to observed variables or indicators. So they have data actually in hand. And by replacing a concept, again, such as resilience by a factor or component in our statistical model, now we can test their hypothesis statistically. And based on this kind of statistical representations, then we can define this very well-known, say, approach, statistical approach, the structural equation modeling, or SCEM, as just like this. So SCEM is a very flexible statistical framework for specifying and testing theory-based relationships between indicators or actual measures or observed variables and factors or components. So that means there are two ways of representing these abstract concepts statistically. Again, one is a factor, the other one is component. This is why this SCEM has two domains. One is factor-based, the other one is component-based. And as these names suggest, in factor-based SCEM, all constructs are now represented as factors, oftentimes common factors, but simply speaking, just factors in this workshop. And in component-based SCEM, all constructs are now represented as components. And very naively speaking, technically, factor-based SCEM combines common factor analysis and path analysis into a single framework. And this is also called covariance-based SCEM in some literature. On the other hand, component-based SCEM combines component analysis, such as principal component analysis, or simply PCA, with path analysis into a single framework. And component-based SCEM is also called variance-based SCEM. And this is a very brief history of these two domains of SCEM. So factor-based SCEM, as I said, have combined factor analysis by Pearson or Spearman or Thurston with path analysis into a single framework in early 70s by Dr. Ureskog and other actually scholars. And their approach is called CSA or covariance structural analysis. And since then, there are remarkably remarkable number of applications of factor-based SCEM, as well as lots of technical extensions of this factor-based SCEM. On the other hand, component-based SCEM combines dimension reduction techniques such as PCA, principal component analysis, or canonical correlation analysis with path analysis, again, maybe early, say, 70s or late 60s by Herman Ward in Sweden into this single framework called partial least squares. And this technique or this method has been technically refined by Lomello in 1989. So this is a very well-known approach to component-based SCEM. And then 2004, another actually the method for component-based SEM has emerged. This is called GSCA, Generalized Structured Component Analysis. And as you may expect, this will be one of the main topics of today's workshop. So simply, the GSA has been used for component-based SEM, where all the constructs are now represented as components. Then you may ask, okay, there might be two different ways of representing concepts statistically in our model. Then what are their characteristics? So let me explain the some main characteristics of factors and components here. And just following the SEM's convention, I'm going to use a circle to indicate a factor. And also in SEM context, factor is same as a latent variable. So these are actually the same thing. And then the fundamental, the assumption or premise of using factors or latent variables is factors or latent variables are representing something that exists in the world. In other words, a factor is an external reality, just based on this very well-known paper. So this is more like the realistic perspective of looking at a latent variable or factor. So, for example, if you think intelligence is something that really exists in the world, maybe in our brain, then you can actually represent this intelligence as a factor. So that means this factor actually they're being out there independently of empirical data. This is in a way very restricted, very actually the restricted assumption. But this is what these authors actually believe the main actually the characteristic of a factor or latent variable, external reality, very strong assumption. And again, this factor or latent variable exists on its own, and then now it's going to actually create empirical data. Again, following the SEM's convention, I'm going to use a box to indicate the observed variable or indicator. So in this example, this factor exists, its own, and then now it's going to generate these three indicators. More precisely, this factor going to actually create the correlational pattern of these three indicators. In other words, this factor or latent variable going to serve as a common cause underlying these indicators, making them covariant or correlated. And here, as you know, these lambdas are simply called factor loadings. Simply these are just regression coefficients of each indicator on a factor. And then these, say, indicators generated by or caused by this factor are called reflective or effect indicators, simply just terminology. And again, what is important here is, first thing, yes, we believe a factor or latent variable represent an external reality. That's first thing. Another one is this factor going to generate these indicators, more specifically, making them covariant or correlated. This is why these reflective indicators should be highly correlated to one another because there is underlying common cause. So these reflective indicators should be homogeneous or look very similar. So this is a main characteristic of factor or latent variable. So this is what I explained so far. A factor represents something real and mind independent that causes or generalized indicators. And this is one example of such characteristic of the factors. This is not this is not a scientific theory or argument at all. This is simply a ruling of a Quebec judge on the racial profiling case that involved police traffic stops in Quebec. And as Austin said, the Quebec is actually where I live. So in Canada. So anyway, so even though this is not the scientific theory at all, this ruling or statement clearly actually shows the nature of factors if this statement is scientific. So let me read it. So racial profiling does exist. It is not a left constructed abstraction. It is not a view of the mind. It is a reality that manifests itself, especially among Black communities. Again, if we believe this is a scientific theory or argument, based on this theory, we may actually represent this construct, racial profiling, as a factor, because racial profiling is clearly external reality and making a lot of some empirical data. So following this argument, then we may consider racial profiling to be represented as a factor like this in our statistical model. And then this racial profiling leads to some empirical manifestations, such as disproportionate car stops or disproportionate minority arrest. So these are now reflective indicators caused by racial profiling. Okay, so then what about components now? So here again, by the convention of SCM, I'm going to use a hexagon to indicate a component, say C. And in the bottom, you can see actually a definition of component. A component simply means a weighted sum of indicators. So in this example, we have again 3 indicators. And then for each indicator, we assign actually this weight. And then this C simply looks like this. Simply you actually assign these weights to these 3 indicators and just sum some of these the weighted indicators that will make a component. This is what I meant by a weighted sum of indicators, and also this is called linear combination of indicators. The same thing. And as you may know, in practice, actually we are creating this kind of components pretty often. For example, if you fix all these weights to 1 in advance, then this C simply equal to the sum of these 3 indicators. Or if you fix these weights to say 1/3, then the C is simply the mean of these 3 indicators. So whenever you compute actually mean or sum of some variables, it's simply making a component. Same idea. So component has the sum or the mean as special case. But in general forms, actually we don't actually fix these weights in advance. But that means once you know these weights, this component will be completely actually determined by these indicators. In this sense, we can say that a component is a deterministic linear function of these indicators. But simply put, just component is determined by these indicators. Oh yeah, also this is a terminology. And then these indicators making this C or component are called composite indicators. And also unlike reflective indicators for factors, these composite indicators may not or don't need to be highly correlated because there's no underlying common cause. There's also differences between reflective and also these composite indicators. Okay, so this is what I explained so far. A component is something that is determined by indicators, and it has been used as a summary or aggregation of indicators. And this is one example about a component body composition. Simply this construct body composition is an aggregation of three things: body fat, muscle, and bone mineral in the body. In other words, now you have these three indicators: first, fat, muscle, and bone, and they are now aggregated to make a more general, say, a concept called body composition. So now these are actually going to make some general concept like body composition, which is known to be related to mental health in psychology. So can you see some main differences between factors and components in our statistical modeling? I hope so. Okay, and then again, naively speaking, in factor-based SEM, simply we have this kind of model. So we have all these constructs: organizational prestige, organizational identification, and affective commitment in different types, something like this. So simply these concepts or constructs are now represented as factors. Then this is now factor-based SEM. And this factor-based SEM has two sub-models. This is called the measurement model. Simply now we're looking at how each factor is related to different indicators. And another sub-model is called the structural model, focusing on the relationships among these factors. On the other hand, in component-based SEM, we're going to actually replace those constructs by hexagons or components. And this kind of model also has measurement model, also called outer model in component-based SEM, the same thing. So now just we're looking at the relationships between each component and its indicators. And also we have, again, the structural model, but now we have only components. And this structural model is also called inner model in component-based SEM. And as I explained later in more detail, actually component-based SEM involves another sub-model called the weighted relation model. But you don't need to worry about this one at this point. I'm going to explain this sub-model again more actually specifically later on. Okay, then you may ask, okay, there are vector-based and component-based SEM using some different statistical representations. And then which one we're going to use between these two, different statistical representations. And all I can say is we should have some scientific theory to justify the choices between factors and components in our model. And if we have this kind of scientific theory to justify our choices, that would be the best scenario. For example, for intelligence, actually there are two different scientific theories right now. One is the very well-known, the classical test theory. This is one scientific theory for intelligence. If you follow this CTT, classical test theory, then we may represent intelligence as a factor. On the other hand, there's another actually scientific theory for intelligence that's called the mutualism. Just we take a look at some mutual associations among different intelligence items. If you think this mutualism is actually more reasonable, then you follow this mutualism, then you can use the component to represent intelligence. So like this, if you have a pretty good scientific theory in advance to justify your use of factors versus components in your statistical model, that is the best scenario. But as we know, in most cases, we don't have scientific theories for back up our choices between these two different statistical representations. And then one heuristic is simply, as I put here, just you try to think hard whether the construct of your interest might be an external reality, something actually that exists in the world. For example, democracy. Do you think the democracy exists as some form in our society? I doubt it. But anyway, if you think that way, sure, then you can use a factor to represent democracy or intelligence or depression, whatever. So you think all these kind of constructs are sort of external realities, just being out there, just like, in natural sciences, sure, gravity or what else? Black holes, sure, they are not directly observable, but we believe they exist. If you have same kind of considerations for other constructs, democracy, intelligence, or depression, sure, then you can use a factor to represent such constructs. And then just you say, hey, these factors are going to now generate empirical data. If you follow that kind of direction of thought, sure, then you can use a factor-based SEM. But simply just you think, no, they are not existing really. They are simply the aggregations of the empirical data. In other words, empirical data or indicators come first. And then they're going to simply make a component, say, representing sort of a general concept. If you actually move in that direction in your statistical modeling, you may use components in your model. And in the literature, factors have been used to represent various psychological constructs or attributes in cognition, personality, emotion, and psychological disorders. I'm not sure that kind of the usage of factors to represent psychological constructs or attributes is a right choice or not, theoretically, but this is what has been done in the literature for many, many decades. And here's some examples of such constructs represented as factors. So general intelligence and the big five, personality traits, self-esteem, depression, or preferences. All these has been represented as factors in the literature. And also, this is why in many academic disciplines or sciences, including psychology and education, simply the SEM has been equated with factor-based SEM. So too many researchers actually in these disciplines handling psychological things, psychological attributes or constructs, simply to them, SEM means factor-based SEM. And also this is why in these disciplines, factor-based SEM has been dominant, basically. On the other hand, as I said, components has been used to represent a summary or a cluster or index of the indicators. And in many places, these indicators simply represent some different, say, elements or different aspects of more general the concept. So as you have seen, say, the fat, the muscle or bone mineral, they actually are representing different aspects of body composition, something like this. And these are two very well-known examples of components we may use in the literature. So SCS is simply aggregation of three variables, and the work stress also sort of a compiling of these different the variables. And as you can see here, these indicators look sort of distinctive to one another, representing distinct actual aspects of SES. Same thing for work stress. So there are different variables or indicators, and they look quite different from each other, just standing for some different aspects or elements of work stress. And then just aggregating them just makes the work stress. And let me give you a few more examples about the components. And these examples have been the motivating examples for my own research. And also I'm going to use this example a few times later of this workshop. So just let me show two more examples of components we may encounter in, say, different disciplines. And this is from the neuroscience. And this is our brain, of course. And then this brain can be divided into a great number of the small cubes, like a three-dimensional entity. And this cube is called a voxel, just like this. It's a three-way kind of a cube. So first voxel, another one, or another one. So like this, brain consists of the so many actually voxels like this. And each voxel is very tiny in size. It's just, the size of one peppercorn. So anyway, and then the using the different modality or different machine, we can actually measure different actually the things on each voxel. For example, if we use fMRI, then we can actually measure the amount of blood oxygen in each voxel. Or if we use MRI, then actually we can measure thickness or volume of each voxel. But just generally speaking, these voxels are simply observed measures or indicators. And then sum of or cluster or aggregation of these voxels now going to make a specific brain region. And this is called an ROI, reasonable interest in neuroscience, such as, say, amygdala or hippocampus. So in this case, these voxels are going to make this ROI, not the other way around. In this sense, we may consider each brain region or ROI as a component rather than a factor. So this might be one example about the component we can have in neuroscience. And another example, say from genetic studies. Of course, I'm not a geneticist at all. I'm just a quant guy. But these are a few things I learned from my collaborations. So here, as you know, in our DNA, there are a bunch of the different genes. And within each gene, say, maybe at this particular location, there might be variation among the population. In other words, there are some different values among people at this particular location of the gene. And this variation is called SNP, single nucleotide polymorphism. Trust me, I have absolutely no idea what this means. But from our perspective, from our quant person perspective, simply SNP is a variable because it has different values among people. So this is now observed measure or indicator. And even in the single gene, there might be multiple SNPs, just like this. So then now we have this kind of SNPs as indicators. And then these SNPs will be aggregated to produce a gene level variation. This is a more biologically plausible. So in other words, gene does not make these individual SNPs. These SNPs are actually going to make gene level variation. This is why we may actually represent this gene as a component or hexagon. So here I just show two actually the examples of components. Say one is from neuroscience, so brain regions or ROIs, and also from genetic studies, genes. These are better actually represented as components. Do you have a question? Actually, I'm not sure about what this means exactly. Could you explain what the text or topic proportions represent?
For example, with a topic model where you have a corpus of text and each topic is a different proportion of that one document, could that
Right,
be considered?
right. Yes, I think so. Then in the case, maybe the aggregation of these things will make some particular kind of the topic or text. Yeah. Okay, so component measures, formative indicators. Good question. No. Let me explain maybe this one after this workshop. But sure, yeah, there are two types of the indicators in factor models. One is reflective that I explained already. The other one is formative indicators. But the formative indicators are also for factors, not for components. This is why I use the term composite indicators. So only composite indicators are used for components. And why the formative indicators are used for factors? Let me explain this one maybe after workshop. Does this sound okay? Or maybe I can show right away, but yeah, okay, later, okay. Thanks. And any other questions? Okay, so let's move on. Okay, so these are some examples about components. Oops. Okay, and these are actually some other examples of components. Maybe we may have some different social sciences, but also let me skip this one. And also I believe this workshop is now being recorded. And also, I'd be happy to share my slides later on if you want. So just let me know. Okay, so as I said, maybe you can just first think whether the construct of interest might be an external reality from the beginning, and that generates empirical data, or just empirical data come first to decide on the some corresponding more general concept. Then you can use a component. But in practice and in many places, actually all we have at hand are simply items or indicators that were, say, developed by someone else. And also we have little idea whether these developers have considered factors or components for these items at all. Just items at hand. And then my heuristic about the choosing between factors and components, given only the items at hand, is this one. Oh yeah, not this one, but is just you look at whether these items or indicators are similar or dissimilar. As I said, the factors serve as a common cause of reflective indicators. That means if these items are quite highly correlated or homogeneous, then we may consider, hey, these items are just developed just based on some common cause or a factor. On the other hand, these items are just quite different or heterogeneous. That means maybe the aggregating is quite distinct. The indicators, so items can make a component. So for exactly same construct, say as I put here, job satisfaction, we may consider a factor or component to represent your job satisfaction given their items. So let me give you some examples of what I just meant here. So this is a job satisfaction, just a definition, so we don't need to worry about this much. And then these are some different questionnaires or measures for job satisfaction. They're all popular in practice, but just let me look at the bottom two, actually the questionnaires for job satisfaction. Okay, and then, so these are actually 5 items, 5 indicators for job satisfaction given in the short index of job satisfaction. So now just let's say we have only these 5 items at hand. And just by looking at these items or indicators, we may decide whether we're going to use a factor or not, or component. Just a heuristic. And as I said, if all these items are sort of highly correlated or similar or homogeneous, that means they are virtually the sort of speaking at different, I'm sorry, not different thing, same thing in different ways. Then we may use a factor. So in other words, say, hey, job satisfaction is a common cause of all these items. This is why these items look quite similar or homogeneous. So in the case, yes, you can use a factor for job satisfaction in the specific questionnaire items. And this is another very well-known, the questionnaire for job satisfaction, Minnesota satisfaction questionnaire. And now let's look at the items or indicators for job satisfaction in this questionnaire. They have 20 different items or indicators for job satisfaction. And now you look at these 20 items, and then to me, actually, these items are not that homogeneous as compared to previous 5 items. So see, the first one, being able to keep busy all the time, or when you look at number 13, it asking about my pay, what the amount of work I do, or it asking about the working conditions and so forth. So that means these items or indicators are not that homogeneous. That means these items or indicators may actually indicate different parts of some general concept, job satisfaction. So then just compiling these 20 indicators or items may make, say, job satisfaction. Then you can use a component to represent job satisfaction given these 20 items. This is my own heuristic, and as I said, it is sort of I don't know, subjective, but this is all I can say. Sure, yes, that's also possible. Yes, yes, of course, yes. So if you have, say, some different sets of the quite homogeneous items, yes, then in the case we may have also the factor to represent each sub set of the indicators. That's possible. Yes, but just in this example, let's assume that we use these 20 items as a whole to represent something like a job satisfaction. In the case, I'm going to use a component. Okay. Another question? It doesn't really matter. It's a reversed or not. That doesn't really matter. Yeah. Just what is important is the meaning of each item and how these items are sort of related to each other, positively or negatively. But if there are some high correlations among these items, then we may actually assume there might be some common cause underlying these highly correlated items. Then we may use the factor. Okay. It's not moving. Okay, so All right, so now I just discussed some characteristics of these two, the different statistical representations of constructs, vectors, and components. And this is why we have these two domains of SCM. And what is important here is these two SCM domains have remained mutually exclusive. That means researchers always represent all their constructs as factors in their model, or they represent all their constructs as components in the model. There's no any sort of exchange of these things in the same model. This is what I mean by mutually exclusive. This is what has been done in the past maybe more than 50 years, I think. And then this is a summary of the characteristics of these two domains that I already explained. So you look at the table later. And also these two SCM domains have their own statistical method for estimating vector-based or component-based models. And when you look at the left-hand side, so these are all the statistical method for estimating vector-based models. And of course, the first one, as I explained before, covariance structure analysis by UNESCO is the most popular, and I think that this is a de facto standard method for estimating vector-based SCM. And though there are a lot of the alternatives here, two-stage least squares, vector score regression, and this some long ugly name, GSCAM, and also consistent partial least squares, or PLSC. So all these methods can be used for vector-based SCM. On the other hand, for component-based SCM, these methods can be used. And GSCA, I know I'm obviously very biased, but GSCA is the most flexible method for component-based SCM, and also very well known and long the established method for component-based SCM is PLS. And actually, the GSCA can have PLS as a special case theoretically. But anyway, so as I said, GSCA is the most flexible method for estimating component-based models. And please try to remember these two names, GSCA for component-based SCM and GSCM for vector-based SCM, because I'm going to use these names over and over. But anyway, yeah, I'm going to repeat them a few more times. Okay, so again, the point here is we have these two different domains of SCM, and these domains have been used very exclusively. So only all constructs as factors or all constructs as components. But as you may actually expect, nowadays, many sciences, including psychology, are becoming interdisciplinary, which means the researchers can have quite different types of constructs from many different disciplines at the same time. And some of them may be better represented as factors, whereas the others are better represented as components. In other words, in practice, there might be a lot of some cases of having both factors and components in the same model.
Yo.
And this is one such, say, example. So here, for simplicity, I'm just only showing us the structural model. So here we have four genes. And now these four genes are affecting depression. And as I discussed, genes may be better represented as the components or aggregations of their corresponding SNPs. On the other hand, depression has been represented as a factor in the literature. So then, in this model, we have both components and a factor at the same time. And this might be more realistic, actually, model in actual research. This model is inspired by work in here, actually, my own research. Actually, this model actually comes from so-called imaging genetics, the studies. So in imaging genetics, just researchers actually assume that any genetic variations may lead to functional variations in different brain regions. And then these brain level variations may lead to some psychological disorders, such as depression. So just they want to link, say, genes to brain regions to actually psychological disorders. So this modeling actually reflects that kind of idea here. So in this example, we have 9 different genes which are known to be related to depression. And also we have one single measure, single indicator for, say, post-traumatic event, PTE. So this is an environment kind of factor or just variable, yeah. Environment variable. And then these product terms are simply indicating each gene and this environment, the variable interaction. So anyway, as I explained, these gene things, not PT, the single measure, they are actually represented as components. And then they are affecting different brain regions. In this example, we have more than 50 brain regions. And also, as we discussed, these brain regions might be represented as components. And then these brain regions are affecting a psychological disorder, depression, which has been represented as a factor. So it's like this. You can have both components and a factor at the same time. And this is sort of to me, actually it's more like maybe common rather than just the exceptional case in the many places, especially all our studies more like becoming interdisciplinary. More another example, but just let me skip this one. Okay, and then you may ask, okay, sure. I mean, there might, as you can see here, there might be some, the cases where you have both components and the factors at the same time. Then why not just using existing SCM method to fit such models? This is a question I have, and then let me show why it is not a good idea to use existing SCM method to fit this kind of model with both factors and components. So this is one example. Again, here I have only the structural model with 2 components, 2 hexagons, gamma 1 and 2, and 2 factors, 2 circles. And when you have this kind of model with both factors and components, there are 3 actually sets of path coefficients, or these arrows in the model. So say this is one set. This set includes all the path coefficients between components only, like between gamma 1 and gamma 2. So this is so-called component path coefficients. And another one is obviously this one. Now, this set includes all the path coefficients connecting factors only. And these path coefficients are also called factor path coefficients. And then the last set is this one. Now these are path coefficients connecting factors and components. And this set is the unique one that only they are given in the model with both components and factors. And now let me show what happens if you use existing SCM method to estimate these path coefficients in the model. This is what happens. So here you have 3 sets of path coefficients. Again, this is a path coefficients between factors only. This is a path coefficients between components only. And then this is a path coefficients between factors and components. And let's say just first we apply factor-based SCM method to estimate all these three sets of path coefficients, such as, say, CSA, covariance, structural analysis, the default one. And also we apply component-based SEM method, such as GSCA, to estimate the same path coefficients. And as you can see here, for these factor path coefficients, connecting factors only, as expected, factor-based SEM method will provide unbiased estimates. But component-based SEM method will provide negatively biased estimate, which means smaller than expected. And this is also called the attenuation of this path coefficient, which is very well known in the literature. And then for these path coefficients between components, also called component path coefficients, factor-based SEM method, such as CSA, will provide positively biased estimates with a larger than the actual parameters. On the other hand, component-based SEM will provide, of course, unbiased estimate because these are path coefficients only for the connecting components. And all these actually the behaviors of this existing method for these two sets of path coefficients are very well known in the literature, as you can see here. There's a question. So let me get it. Oh, okay, that's a good question. Let me get this one, okay? Let me get to this one a bit later, okay? I'll explain the difference between PSSEM and GSA later on. But the short answer is yes. Okay. Basically, the GSA and the PLS actually will provide quite similar results under some condition. But let me explain what this condition is about and the behaviors of these two methods later on. Okay, and then the last one, the unique set of path coefficients connecting factors and components. Factor-based SEM method will provide positively biased estimate. On the other hand, component-based SEM method will provide negatively biased estimate. So then, this is a more recent finding by these authors. And then the point here is, when you actually use the existing method for estimating models with both factors and components, the existing method will always provide biased estimates of some parameters, as you can see here in this table. This is why this is not a good idea to apply simply the same existing method to estimate such models with both factors and components. And this is why this new method, IGSCA, or integrated generalized structural component analysis, has been proposed to develop to estimate the models with both factors and components. And technically, this method combines two existing methods. I'm not sure you still remember these two names, but the GSA is for component-based SEM, and GSM is for factor-based SEM. Simply it combines these two existing methods into a single framework. And I'll give you a little more explanations about these things later on. But anyway, here, so we have this table before, and then GSA for component-based SEM and GSM for factor-based SEM. And these two methods have been combined into IGSCA. So now we have three ugly names all involve something like a GSCA. So first, GSA for component-based SEM, GSAM for factor-based SEM, and then this IGSCA for estimating hybrid models with both factors and components at the same time. And then now we have GSA SEM. So GSA SEM is an umbrella term that actually they are representing these three methods at the same time. In other words, this GSA-SCM can be used for estimating models with components by using GSA, or models with factors by using GSA-M, or this hybrid model with both factors and components by the IGSCA. So this is the main topic of today's workshop, and that is sort of some conceptual underpinnings of what GSA-SCM is about. And if you want to use this GSA-SCM in practice, sure, we're going to use this software called GSA Pro. Simply you go to this website. Let me open it. Is it working? Okay, so here, then this is a website of the software, and then simply as you download GSA Pro, either for Windows or Macs on your computer, and yeah, and that's it. And then this is actually the free of charge, and I can assure you that this software will remain free forever. I don't have any intention to make money out of the software. So, but at the same time, we keep updating the software on a regular basis. Okay, so you can just download this software on your computer, and then you can use it. And also you can go to this tutorial session, and also it has a user manual for Windows or for Mac. So it actually explained a lot of things in detail about all different analysis in GSA-SCM. Here's another question. Yeah, maybe I can send my slides to the conference committee, and then maybe the committee may find some way of distributing the slides, I guess. Okay, so, and then you will see this is quite user-friendly. As you can see, simply you draw your structural model only, and you click the button run, then it shows all the results. And yeah, I will show you how to use this one for different applications later on. And this is a show-off. This shows some traffic data on how many people having, say, visiting the website, this website of the software. So that means these traffic data are not exactly showing the number of actual users of the software, but I hope that there are some strong positive correlation between this traffic data and the actual users, so the number of users. But anyway, as you can see here, a lot of people are using from all different countries right now, and there might be a lot of applications already. And yeah, of course, there might be some work I need to do more for promoting in, say, China or Russia and so forth. But anyway, so the point is, the software has been used by the many researchers across from different countries, as you can see here. Okay, so time is now. Okay, yeah. So this is sort of the first kind of a description of what this GSA-SCM is about. Okay, so just here, let's take maybe 10-minute break, and then we come back for more specific say descriptions of these three methods in GSA-SCM, and also the use of software for each case. So do you have any questions so far? Okay, then maybe you can come back in 10 minutes. So in my time, that would be 8:15. Is it okay? Okay, so then I will see you in 10 minutes. Thank you. Okay, so welcome back. So now let's move on the some more specific topics of GSSEM. So as I said, there are three different methods under this the umbrella term. So first one is GSCA for component-based SCM, and another one is the GSM for factor-based SCM. And then the last one is IGSCA for hybrid models, both factors and components. So first, let's look at the GSCA for component-based SCM. So I'm going to explain the GSCA in terms of these three things: model specification and primary estimation, and assessment of model fit. And again, simply put, the GSCA can be used to estimate this kind of model. So all your constructs are now components. So for the model specification in GSCA, I'm going to use this simple example where we have two components. So gamma 1 and gamma 2. So we have two components just for illustration, and each of them is linked to two indicators. And here, C1, C2, or C3 and C4. These are simply component loadings, which indicate the influences of each component on their own indicators. More like a factor loading, it's the same thing. And then B is a path coefficient, now connecting these two components. Okay, so in this example, say there are actually the three sum models in GSA. The first one is this one, as I briefly discussed. Simply the measurement model, looking at the say the associations between indicators and their component. And in general, this measurement model in GSA can be expressed this way in matrix notation. You don't need to worry about this equation itself, but simply put, this equation express this kind of the associations between components and their indicators. So here, this Z vector consists of all, say, indicators, and the C matrix now consists of all component loadings, the effects of components on their indicators. And then this gamma vector consists of all the components. That's it. But again, no worries about this equation itself. And for this the example, this measurement model, this equation looks just like this. But again, no worries. So this is now the subset. I'm sorry, the one submodel of GSCA, and then this is now the structural model between only components. And again, this structural model can be expressed as this form in matrix notation. So here, this B matrix now consists of all path coefficients connecting components. And for this particular example, this structural model just looks like this. Again, no worries. So there are two now sum models. And then there is another one. As I said, a component is defined as a weighted sum of indicators. So we need to explicitly incorporate this, say, definition of component in the modeling process. This is why we have now these weights. So these weights are now assigned to these indicators, Z1 and Z2, to make this gamma 1 a component. Same thing for this part. Again, simply shows, yes, a component is a weighted sum of indicators. That's all. Just like this, gamma 1 is expressed this way, gamma 2 is simply this one. And in general, this is called the weighted relation model, and this model can be expressed as this one. So this W matrix consists of all these component weights. Okay, and for specifically this model, can have this kind of model. But okay, again, no worries. So then the bottom line is in GSCA, we have these three sub-models to specify a component-based model as a whole. And in GSCA, by combining these three different sub-models in some different ways, GSA can provide different types of components. You will see some examples. So first, say, type of components are called nomological components. So simply terminology. Very simply put, if you have all these three sub-models in your model, so measurement, structure, and weighted relation model, at the same time, then the corresponding components are called nomological. That's it, that's a terminology. Let me use this example again. So always in GSA, this weighted relation model is actually is necessary. It must be given because we're dealing with components. So this is a weighted relation model. So again, each component is simply weighted composite of these indicators. And then now you have measurement model like this. And as I explained, these C's all showing the influences of components on their indicators. So this is about measurement model. And at the same time now we have structural model like this. So that means this gamma 1 is also the influences gamma 2. So by having all these three sub-models at the same time, our components are going to explain their own indicators, as you can see, by these loadings in measurement model. At the same time, these components are going to explain dependent actually components. So simply put, your components will going to explain indicators as well as other components. That kind of components are called nomological. That's it. Or very simply put, just you keep all the three sub-models. That's it. Then those corresponding components are nomological. And we have another type of components in general speaking in component-based SEM. That type is canonical components. In this case, we have only two sub-models. One is the weighted relation model, and another one is structural model. So if you keep only these two sub-models, the corresponding components are called canonical components. Again, let me use this example. So always we need the weighted relation model to define a component. And then now you keep only the structural model like this. No measurement model here. So that means this gamma 1 is now explains only another component, not their indicators. If you have this kind of component, or if you have these two sub-models only, weighted relation and structural models, then the corresponding components, like as you can see in this example, are called canonical. Actually, if you are familiar with canonical correlation analysis, very well known multivariate statistical analysis method, this model simply looks like canonical correlation analysis with only one component per set of indicators. This is why this kind of component is called canonical component. And now you have these two types of components at hand, then which one will be used over which one? Well, can you use both? Yes, but as I put here, we always recommending using nomological components over canonical components in GSCA. There are a few reasons. The first one is, as you can see here, canonical components may be afflicted by potential interpretational confounding. Simply means the meaning of canonical components can change depending on actually the structural model we specify. Let me explain this a little bit more using this example. So here, as I said, this gamma 1 is a component that explains gamma 2 very well. Okay, this is how we construct this gamma 1. But in this case, simply you replace gamma 2 by another, actually the component, say gamma 3. Then now the meaning of gamma 1 changes. Simply now gamma 1 is a component that explains gamma 3 well, not gamma 2. So like this, in canonical components, their meanings can change depending on which components they're going to explain. This is called the potential interpretational confounding. I have about 2 questions. Okay. This is about the slides. This is it seems okay, it's moving. Okay, so this is one problem, but the canonical components are actually less sensitive to such interpretation confounding issue because the always nomological components are going to explain their own indicators to some extent. But this is all I can say for now. And also, the canonical components have lower actually prediction power than nomological components. Actually, in the past, some researchers believe that canonical components may have a higher prediction power than nomological components, but this is not the case, as is shown in this paper. Even for predicting future observations, canonical components are better. So this is why there is, again, as I said, if you have choose nomological versus canonical, the answer is very straightforward. Just use nomological components all the time. Nomological components are actually less sensitive to potential interpretation confounding, as well as it has a higher prediction power. And also it's quite more, how can I put it? It's actually more reliable actually than the canonical components. This is why the nomological components have higher prediction power, which means smaller variance for future observations. Okay, and then there's actually another type of components that's called principal components, as in PCA, but this is simply the special case of nomological components, just like this. So we don't have any structural model. Simply these two components are correlated. So no structural model, but this model just looks like the principal component analysis for each set of indicators. So each component, we're going to explain their own indicators so well. That's all. So this is simply the special case of nomological components. Okay, so that's to sum up. In GSCA, we have these 3 sub-models: measurement, structure, and weighted relation models. And then GSCA combines these 3 sub-models into single framework. Just let me skip this one. This is not that important, but like this in the end. So simply we combine all these 3 sub-models into this single actually equation in the end. Just one equation can be used to accommodate all different types of the component-based models. This is sort of the beauty of GSCA in terms of model specification. And here is weights and the loadings in C and path coefficients. They are actually the parameters of GSCA model. And to estimate these GSCA parameters, we're going to actually minimize this sum of these residual terms in the sample we have. In other words, just we want to minimize this least squares objective function. just like in linear regression. I'm not going to explain further. Simply just we have one single optimization function, which is quite similar to just the least squares linear regression problem. And just we develop some alternating least squares algorithm to minimize this objective function consistently. Again, I'm not going to explain this algorithm in detail here, but this algorithm will estimate all parameters simultaneously. So upon convergence of this algorithm, we have all the estimates of parameter at once. In the sense, GSA is a full information method, which means we use all the data available in different equations at the same time for estimation of parameters. And so this algorithm is a default algorithm for the software GSA Pro. And at the same time, there is also a Bayesian estimation method for GSA, but this is certainly outside of the scope of this workshop. Okay, and so here actually, when you estimate the parameters in GSA, we don't impose any distribution assumption such as normality on indicators. So this parameter estimation procedure is distribution free, which is nice, but at the same time, this is why you also use this bootstrap method for estimating the standard errors or confidence intervals of parameter estimate. And particularly, we're going to use this percentile bootstrap method to get these standard errors and confidence intervals. So everything's okay. I just think went through all these some technical things rather briefly, but just let me know if you have any questions about this technical underpinnings of GSA. Okay, and then now you have all these parameter estimates, and then just we want to test or you want to examine how good my model for the data I have or for future observations. So this is about the assessment of model fit. And the GSA provides several overall model fit measures to evaluate the model as a whole. The first two indices are fit and A-fit. Fit is more like R squared, and the A-fit is more like adjusted R squared in linear regression. In other words, fit explains the total variance of the sample I have. In other words, in sample data explained by the model I specify. And it's between the 0 and 1, so the larger the value, the more variance is explained. And A-fit, just like just R squared, it takes into account model complexity or number of parameters. And A-fit is simply used for comparing different models. So in that sense, A-fit is comparative, actually, the fit index. On the other hand, fit is absolute, the fit index, because its value has some meaning, as I explained, like R squared. And then GFI and SRMR, if you are familiar with the factor-based SEM, these two indices sound familiar to you. And GFI and SRMR actually shows how close the in-sample covariances and then implied covariance estimates, so the covariances reproduced by the model parameter estimates. And then we have some rule of thumbs of using these GFI and SRMR values for checking the acceptable model fit. For example, if sample size is around 100, then you may use the rule of thumb, the recommendations or cutoff for acceptable model fit. For example, if GIF is equal to or greater than 0.89 and SRMR is smaller than or equal to 0.09. If these two things happen at the same time, then we may say our model may be acceptable in fit. On the other hand, if sample size is greater than 100, then we can use this cutoff of GFI or this cutoff of SRMR. So either one can indicate an acceptable level of model fit when you have large sample size greater than 100. So this is how you interpret these values. And then these four model indices actually focusing on the sample data, the sample at hand. In other words, now we are looking at only in-sample data. But sometimes also we want to check how our model actually is good for predicting future observations or unseen observations called an out of sample. So this index OPE can be used for checking the prediction power of the model I have, say for out of sample or future observations. And OP is also a comparative fit index. So this value itself doesn't tell you much, but OP can be used for comparing different models' prediction powers. So the smaller is actually the better prediction power. And also the bottom line of OP value is actually 1. So if your model's OP is equal to 1, that means your model's prediction power is simply same as the null model's prediction power. So there's no point of using your model for prediction of future observations. So the bottom line is your model should have an OP value smaller than 1. Okay, so these are several overall model fit measures we can use for checking the model's goodness of fit. And also the GSA provides local fit measures. So we're looking at each sub-model at a time. So fit M, this is for fit value for measurement model. Fit S, this is a fit value for structural model. So we just look at each sub-model at a time. And also OPM, this is a prediction power of our measurement model. And OPS, this is a prediction power of our structural model. So there are a bunch of different fit measures. So this is a summary of those overall and local fit indices used in GSCA. So absolute simply means the index value has a meaning. Comparative means the index can be used only for comparing different models in terms of the in-sample explanation, like A-fit, or in terms of the out-of-sample prediction, like OPE. And also we have these local measures. Okay. So, and at the same time, now you need to look at the each, say, sub-model at a time. So just you need to check the quality of your measurement model or the quality of your structural model. So first look at the measurement model with only components. This is because the component-based model. So you can check dimensionality, which means if you assume a unidimensional component, in other words, you assume only one component per set of indicators, then you can check this unidimensionality based on the Kaiser criterion, also known as the eigenvalue criterion. So the first component should have only the first component should have the eigenvalue greater than 1. And all the other components should have the eigenvalues smaller than 1. As you know, it's a PCA one-factor analysis. And also the proportional variance explained can be used to check this unidimensionality. In other words, the single component should explain at least 70% of the indicator's variance based on this the recommendation. And also importantly, we're going to look at statistical significance and also relevance of component loadings in the measurement model. Again, loadings are simply indicating the influences of components on their indicators. And these loadings should be statistically significant. And also here, relevance means it should be large. So if you have large loading values, that means, yes, the corresponding indicators are more relevant to the component. So we can check the bootstrap confidence intervals for checking the statistical significance and also to look the sizes of loading estimates. So by doing these things, just we can check the quality of the measurement model as a whole. Same thing for the structural model with the components only. First, you can check the multicollinearity of independent components. And as you know, like in linear regression, if you have the multicollinearity of components, then the estimate, especially path coefficient estimate, will be very unreliable. So then this is why we're going to check if there are any high correlations among the components. So multicollinearity. And very well-known index for checking multicollinearity is, of course, VIF, variance inflation factor. And some recommendation is VIF should be smaller than 3. And also we can check the statistical significance and also sizes of path coefficients. And then the other are simply R squared, like a linear regression for dependent component. And also you can check the effect size. These are quite straightforward, just in a linear regression. So I'm not going to explain further. Okay, so by looking at some of these different sort of metrics, we can check the quality of structural model and also measurement model with components only in GSCA. Then there are also the alternatives to component-based SEM, as I explained before. So, and then I put some, the alternatives to component-based SEM here. But the first one is the best known, and also this is also quite popular in many different disciplines nowadays. So partial least squares, or simply PLS, SEM, can be used also for component-based SEM. In other words, the PLS SEM or PLS is the main competitor to GSCA. And this PLS or PLS SEM has these software programs. So Smart PLS, this is commercial, but this is a really beautiful software, and it's very flexible and easy to use. And CSAM, this is our package, this is free, and this is still pretty okay to use. So then let me briefly explain the main characteristics of PLS, and then when we're going to use between GSCA and PLS or PLS-SEM. Okay, so in terms of model specification and primary estimation, I'm going to explain this PLS or PLS-SEM or PLS path modeling. Again, simply put, I'm going to use the same example. Very simply put, PLS also actually consider exactly same 3 sub-models: measurement model, structural model, and weighted relation model, as I explained for GSCA. Then the main difference between PLS and GSA is in PLS, we don't combine these 3 sub-models into a single equation. This is what we have done for GSCA, right? So in GSCA, we simply combine these 3 sub-models into this single one, right? But this kind of thing is not happening in PLS. That's the main technical difference between GSA and the PLS. And consequently, PLS actually carries out 2 stages sequentially or separately to estimate all parameters. Well, I'm not going to explain this primary estimation PLS in detail. This is not the PLS workshop. But simply put, in the first step, the PLS estimate component weights. And once you know component weights, then also you can estimate components. So in the first stage, I estimate weights and components. And then given these components, in the second stage, PLS estimate the other parameters, such as path coefficients and loadings. And yeah, just let me skip this one. But if you are familiar with the PLS, in PLS, there are two different ways of estimating component weights in stage 1, mode A and mode B. Again, if you are not familiar with PLS, you don't need to worry anything. But simply put, mode A actually is the same way of the creating or estimating nomological components in GSA. On the other hand, mode B is actually same as estimating canonical components in GSA. Just a terminology difference. Okay, so let me skip this one. Okay, let me skip this one. And then the main issue, maybe we have with the PLS estimation, well, just in general speaking, just that the PLS has this kind of important, actually, the issues in practice. That is, PLS can handle very restricted form of the relationships between components and indicators. As you can see here first, in PLS, the model must be unidimensional. So it has only one component per set of indicators. In other words, the PLS cannot handle multidimensional components. And also, structural model must be always given in PLS. Without structural model, PLS cannot actually estimate anything. So in other words, if you have only the measurement model at hand, PLS cannot be used. And also in PLS, all structural model must include unidimensional relationships between components only. Let me explain this one very shortly. And also, PLS does not allow imposing constraints on parameters. So just imposing constraints on parameters is impossible in PLS. Good question. My short answer is no. And I'll explain this one later, but answer is no. PLS SEM can be used only for estimating component-based models. And so in that sense, actually the GSA SEM is different from PLS SEM. GSA SEM is the flexible umbrella term, having all these different methods for component-based model, vector-based model, and the hybrid model. But PLS SEM is only for component-based model. Okay, so let me explain these restrictions maybe again here. Oops, this was so slow now. My computer becomes really warm. Okay, so this is what I explained in the previous slide. So PLS actually requires this kind of model only. So in other words, again, only one component per set of indicators. That's it. This is what I meant by unidimensional model. That means PLS actually cannot estimate this kind of cross-loadings. So in other words, for this indicator, we have these two actually components. So this kind of thing is not allowed in PLS. Of course, GSA has no issue with estimate this kind of cross loadings. And also, as I said, PLS can handle this kind of measurement model only. It always requires structural model, kind of directional relationships between components are required. And also the PLS actually allows only this kind of a unidimensional kind of model. This one of X, C2, this one of X, C3, or this one of X, C3, this kind of unidimensional, not unidimensional, unidirectional relationships are only allowed in PLS. In other words, PLS can handle this kind of bidirectional relationships. Of course, no issue about this thing with the GSCA. And also the PLS always required having this kind of unconstrained model. So these are the stuff unconstrained, so separate path coefficients. But in some cases, you can fix maybe one path coefficient or other parameters to some constant, maybe like this. So this is now fixed, but PLS can handle this kind of constrained model. Or sometimes also we can just assume that these path coefficients are identical, but imposing such an equality constraint is not allowed in PLS. But GSA has no problems of estimating these constrained models. So this is my answer for the choices between GSCA and PLS for component-based SCEM. Simply put, I know I'm very biased, but simply put, I'm going to recommend the using GSCA over PLS all the time. I don't see any actually cases where PLS performs better than GSCA. In a way, technically, GSCA can has PLS as a special case, as I explained so far. PLS can be used only very restricted type of models. As I put here, if your model is unidimensional and unidirectional and unconstrained, yeah, you may consider using PLS. In this case, both GSCA and PLS will likely produce very similar actually primary estimates, sometimes almost identical estimates. But even in this case, GSCA still actually tends to provide smaller standard errors. In other words, GSCA's estimates can be more reliable and increasing statistical power. This is all very known in the literature. And at the same time, GSCA can provide overall goodness of the measures, which PLS cannot offer. So again, first we can use GSCA all the time. There's no actually, point of using PLS anymore. However, one practical consideration is actually software. PLS, as I said, has a very good software, especially smart PLS. Yeah, I should say this is a beautiful actually the software, and its developers they are good friends of mine. So I have nothing against this software. I love this one, but it is commercial, and but you will see very shortly, GSA Pro, the software for GSA, also actually working pretty nicely in many actually cases. So again, I think the GSA will be the complete alternative to PLS. So now let me show how to run the GSA with this software. Okay, another question. That's right. Yeah. Also, actually, the GSA has actually R package. It's called Jessica. Yes. But again, in such say conditions where the model is unconstrained and unidimensional and unidirectional, sure, GSA still provides more reliable estimates. Okay, so okay, so now, so one example about GSA. So here we have 4 constructs: socioeconomic status, so SAS, and the health behavior, and the health status, and job satisfaction of South Korean workers with disabilities. So there are 4 constructs. And then so we consider all these, the constructs, to be represented as components, because I will show you on the next slide. Their indicators, so items, seems to be quite heterogeneous, which means these indicators are representing the different aspects of their constructs. This is why we use components. And the sample size is over 1,200. Oh, no, this is just the paper written in Korean, so we need to worry about this one. This is the paper. And then this is actually those items or indicators for these 4 constructs. As I explained, the SES, sure, it can be expressed as the component. And then health behavior, yeah, this is only single measure, so no need to worry about these things. And then these 3 items for health status. And when you look at these 3 items, they look quite kind of heterogeneous. This is why we use a component to represent health status. And also same thing for job satisfaction now. See, all these actually different items, so indicators for job satisfaction seem to say stand for different aspects of the job satisfaction. So simply aggregating them will make this a construct job satisfaction. This is why we use a component in this example. And then just you open up this software and just actually you draw only structural model like this. And then let me show how to run these things. So I'm going to open up this software. So this is the first page, the interface. And then to start, actually, we're going to create a new project because this is a new one. So of course, and before actually running the software, you need to first make your own data file. In say most cases in Excel, or you can use it. You can make it in text or CSV. But I just use an Excel file. So this is actually the data set I created for this example. So in this Excel file, always the first row will include these variable names. And then the following rows will have the different values of each of these columns. So let's say this is the only one required. So this is data file for this example. Okay, so again, I'm going to create a new project here. So then just you go to this icon on top menu, new project, and then just you name your project. So maybe workshop test 1. Oh, this name already exists. So okay, then workshop test 1. How about this one? Okay, then now this file name does not exist. So this is now a unique file name for this new project. And then I'm going to actually load this data file. So file, and then say option examples. Okay, so this is a data file. So in Excel format, this is what you have seen. Just click on, then that's it, and just okay. Yeah, this just no worry about this. This is missing data values. Okay, then this is done. Now your data file is kind of saved in this software. And to check your data file, you can go to this bottom tab, like a data, and just you click on this tab. then now you can see all your data file is successfully actually loaded here. So it shows all these variable names and then these values. Okay, now you go back to this model tab to draw the structural model among components. And this is actually what you have seen. So I'm going to draw this structural model with the 4 components here. So then first you go to here on top, there is a menu, analysis. And then now you have these 3 choices, GSCA, GSM, and IGSCA. And thus you can choose, of course, GSCA, and then there are a bunch of different actually I say more advanced actual analysis in GSCA. But for today's workshop, I'm going to go for just basic one, so basic GSCA, and then we have only one group, so single group. That's it. And then now, when you look at this left, say, panel, you see all these different items to specify your model. So in the example, we have 4 components. Then I'm going to draw 4 components on this main window. So first you go here, icon, add component, just click on this. And then just you create 4 components like this, just 4 clicks. That's it. And then now you need to actually specify the measurement model part. In other words, just you need to link indicators to each of these components. So for that, just you double click on each hexagon. And then now you can see the list of variables in your data file. Maybe you can rename your components, say SCS. And then in this example, these 3 variables or 3 indicators are actually 4 indicators. So now I assign these 3 indicators. And if you don't touch anything else, then it's automatically nomological component. But if you want to create canonical components, so for some reason, just you can click on this one. But as I said, in practice, I don't see much benefit of using canonical component. Okay, that's it. Then now you specify SCS, and this color now becomes less dark. Okay, the same thing for the other components. So this is now health, say health behavior, and it has only single measure. This one, the exercise time. So I just put this indicator. So in this case, this component is same as the single measure. And then this one is now health status, and it has 3 indicators. So like this. And that's it. And then the last one, job satisfaction, and it has 9 different indicators. So just you assign them to job satisfaction. Done. So now when you look at this right-hand side window, it shows this entire measurement model. So which component is linked to which, say, the indicators. And then to finish your model specification, now you put the path coefficients. So now you go here again on the left-hand side, just you choose add path, and then just you add path coefficients. It's always from independent to dependent, the variable, just like this. Yeah, this is what we have in this example. I guess this one, and there might be another one here. Okay, then done. Now we're done actually specifying the entire model, both structural and the measurement model. That's it. And then just you push this button, run. Done. Now, automatically it runs 100 bootstrap samples. So it shows this algorithm converged in 7 iterations, very fast, very efficient. And then now you have this model fit measures, as I explained, fit A fit, and this local fit measures, and then GFI, SRMR, and based on those some rule of thumb recommendations, this model seems to be acceptable. And that is weights and their estimates and the standard error and 95% confidence interval. And if 0, as you know, if 0 is inside of this confidence intervals, that means corresponding the parameters are not statistically significant. Same thing for these component loadings, loading estimates, and then confidence intervals. And all these loadings are statistically significant, and also the are large in size. And then these are path coefficients and their estimates, and then 95% confidence intervals. So in this case, the first one is a statistically significant, but not next one. Something like this. The interpretation of this statistical significance is straightforward. Okay, so these are the result. And then if you want to check the more detailed result, you can go here, view result, and then it explains the a lot more actually information about, say, BIF or the effect size measures and so forth that I explained already. So just like this. So I'm not going to repeat these things, and for more details, please look at the user's actually manual. But the point is, it's straightforward to use, and I believe this is quite user-friendly. So any questions? Everything's okay? Okay, so that's it. And let's see what is now. Okay, we have 1 hour left. Maybe just let me just oh, there's a question. Let's see. Oh, thank you. Okay, so actually, I was supposed to have another break here, but just let me move on if you don't mind. And then if we can finish a little bit early, maybe that's fine. So just let me move on to the other two. The method in GSA-SEM. But I'll be more brief because already you now have lots of background knowledge for the other two actually method. So let's look at the next one, GSA-M. As I highlighted a few times, GSA-M is used for estimating factor-based models. So all your constructs are now factors. So I'm going to explain the GSA-M in terms of model specification and model fit assessment. So simply put, GSA-M is used for estimating models with the factors only. And so in other words, so we can fit this kind of model using GSA-M. So all these constructs are now factors. And in model specification, again, GSA-M has these 3 sub-models. The measurement model, simply this is the factor analysis model. So this is a indicator vector. And then now the C consists of all factor loadings. And this gamma has all factors. And then this term is, as you may know, simply this term indicates the uniqueness term. Here, this D is the matrix of unique loadings, and this U consists of unique factors. So this is simply the quite familiar factor analytic model for measurement model, and then structural model, same as before, but the difference is now this gamma consists of factors, and then this B now consists of all path coefficients connecting factors only. So factor path coefficients. And then one unique, actually the sum model for GSA-M is this one. Still, GSA-M has this weighted relation model. This is a bit different from the sort of typical factor analytic models. Here in GSA-M, this factor is now again defined as weighted. So W has weights, weighted sum of indicators, but with all these uniqueness term removed. In this way of the expressing factors is a bit different from maximum likely estimation of factor. But this way is not that new. Actually, maybe before actually the maximum likely estimation is popular, this is one way of actually estimating factors, and this way is very well discussed in many actually the factor analysis textbooks, such as this Mulex factor analysis textbook. So maybe specifically if you apply principal axis factoring, then actually this factor is expressed this way. So again, no worries too much. This is one way of expressing factors. That's all. This is why the GSM can provide unbiased estimates of parameters in factor-based models. And one advantage of using GSM is it does not suffer from non-convergence. And also, it does not suffer from improper solutions. As you may know, when you apply some factor-based SEM method, such as covariance structure analysis, sometimes you may have some bizarre-looking estimates. For example, the negative variance estimate. But as you know, variance should be always non-negative, right? Because variance is a squared term. So it shouldn't be actually negative. But sometimes in covariance structure analysis, yes, we have such improper solution, negative variance estimate, or sometimes you can have the correlation estimate greater than 1 in absolute value. But as you know, correlation should be always between 1 and -1. But that can happen. And some of the more actually the conventional, the factor-based method. But GSM does not have that kind of problem. And also the GSM provides overlapping measures such as GFI and SRMR. And then just we can use this rule of thumb, the guidelines, which are quite popular in factor-based SEM literature. And also you can check the quality of measurement model with factors only. And all these actually metrics are quite familiar to the factor-based actually the SEM users. So you can check reliability such as Cronbach alpha or composite reliability. Also you can check the conversion validity using this AVE, average variance explained. And also you can check the discriminant validity by looking at this hetero trait and mono trait, or HT-MT ratio. Again, I'm not going to explain all this in detail because this is quite well known in SEM literature. But the point is, yes, GSM also provides these metrics to check the quality of measurement model. Of course, we're going to look at statistical significance and the sizes of factor loadings. Yeah, this is straightforward. And also we can check the structural model. So just by looking at multiple linearity of independent factors or statistical significance and the sizes of path coefficients, and also R squared for each dependent factor or effect sizes. Okay. So then, as I explained earlier, there are a bunch of different statistical methods for factor-based SEM, as you can see here. And then the bottom one is the latest development for factor-based SEM. And then, as you know, there are a bunch of different very nice software programs, free or commercial. So these are some the software programs for factor-based SEM. And then you can ask, then do we need to use a GSM over this existing method for factor-based SEM? My answer is no, not really. Honestly, simply just you can use actually existing method. They have the very well developed for decades, and yeah, precisely actually they have actually more flexible functions compared to GSM in many different ways. So in practice, you don't need to apply GSM over the existing factor-based method. But there might be some cases like where you have a very serious non-convergent issue or improper solutions that may not be dealt with by the existing vector-based method. And in those cases, you may consider using GSM, but in most cases, in practice, I don't see actually the benefits of the using GSM for estimating vector-based model. But then why I explain GSM? Because GSM is a very important actually the part of the another actually the GSM SCM method, which is IGSA. Okay, so anyway, so I'm going to say show how to run or how to apply GSM for the vector-based model using the software. Good question. No. The short answer is no. Maybe this is a one actually. There are some ways of checking the some model modification, but still there's actually little development in model modification models. So no. And this is also the one practical reason why I'm not recommending the using GSM over, say, some more the conventional method. Yes, that's a good point. Okay, so in this example, I have again four constructs: consumer satisfaction, brand attitude, brand preference, and the purchase intention. And these data include 195 the consumers of dairy products in Morocco. So this is sample size. And here I'm going to actually represent these four constructs as factors because this is known that these psychological attributes, like feelings or beliefs or preferences, can be represented as factors in the literature. So, and also, when you look at these items or indicators for these four the constructs, say for example, for customer satisfaction, these items actually look kind of homogeneous or say similar, which means there might be some underlying common cause, say consumer satisfaction, and making these indicators covariant or correlating. Same thing for the other constructs. This is why we consider using factors to represent these constructs. So again, in GSA Pro, simply now you actually the same as before, just you draw the structural model, but in this case, we have only factors. In other words, we have only these circles. So again, just let me show how to do this thing in GSCA. So now I'm going to create another new project. So say this is a workshop test 2. We have one more question. Oh, okay, this is email address. And then I'm going to bring up the data file. This one. Okay, then okay. So again, maybe you can check the data file. So here, so we have all these different the indicator names, variable names, and then these values. So now you specify your structural model with factors only. So then to run GSAM, the same place, you go to analysis on the top and just choose second option, GSAM. It has only basic, say, function, basic GSAM, and then single group. So now in this, the left panel, you have now this option, add factor. So just you click on this one, and then just you click 4 times because I have 4 factors in the example. And then the same as before, just you specify the measurement model. between indicators and each factor. So say this is now customer satisfaction, and just you allocate these 5 indicators. Same thing. Now this is brand preference. And then just you assign these 4 indicators. And another one. Now this is brand attitude. And then there are how many? 3 indicators for this factor. And then the last one is purchase intention. And then just you assign these 4 indicators. Done with the measurement model with the factors. And then just same as before, simply you add path coefficients always from independent to dependent. Same thing. Another one like this. Maybe another one like this. Okay, so then now you're done with all model specification. Just then you press run. And voila, now you have these all the parameter estimates and then model fit measures. Again, based on this GFI and SRMR, this model seems to be acceptable because SRMR is smaller than 0.08 and GFI is greater than 0.95 and so forth. And then also load, these are now all factor loading estimates, and then 95% confidence intervals. And then all these are path coefficients connecting these 4 factors and so forth. Okay, so this is about it. Very straightforward, I think. Okay, now let me move on to the last topic. The last one. Personally, the most exciting one, the IGCA integrated the generalized structural component analysis for estimating hybrid models with both factors and components. So in other words, we can fit this kind of model. So you have factors in circles and a component in hexagon. Okay, just let me again briefly explain the IGCA in terms of these 2, say, aspects. But already you have all the necessary background knowledges for IGCA. So let me go very briefly with these the 2 things. So in model specification again, IGCA is a combination of GSCA and GSAM. So then simply combines these 2 sets of sum models. So this is one set for GSCA, and this is another set for GSAM. Simply now you combine these 2 sets of sum models into single framework. Then it will give the 3 sum models for IGCA. So here, so this is a measurement model for IGCA. And when you look at this one, the first one, this is actually from GSCA. And then this bottom one, this is from GSCA-M. So you combine these 2 measurement models for GSCA and GSM into single one, like this. Then this is the measurement model for IGCA. Same thing for the other sum models. So as I said, still IGCA has these 3 sum models. And then all these 3 sum models are combined into this single equation. Okay, and then IGCA provides overall model fit measures such as GFI and then SRMR. And based on these values, you may see whether your model with both factors and components can be acceptable in model fit. And then we have a sort of a specific guidelines or cut points for acceptable model fit in different sample sizes. So please look at these slides And also I will show some very good reference about these things later on. And also we have actually the measurement model. Actually, there are two parts. One part with only components, another part with only factors. Let me go back to this example. So here, so we have measurement model between indicators and factors, right? So we have this kind of measurement model involving factors, and then this measurement model involving components. So then just we're going to apply the metrics we used for GSCA here. And then the other measurement model part involving factors, we're going to use the metric we used for GSCA M, which all already we have discussed. So this is now the measurement model part with components. So then this is all I explained when we talk about the GSCA. So these are same, actually the metrics we can use. So I'm not going to repeat. Same thing, this is now the metrics for checking measurement model with factors. All the same thing. And then structural model, yes, we're going to check the multiple linearity of components or factors and the path coefficients, the statistical significance and the relevance and so forth. This is all we have discussed. So this is why I was saying that already you have all the necessary background knowledges for following IGCA. So nice. Okay, then you may ask, okay, so IGSA can be used for estimating models, both factors and components. And are there any alternatives to IGSA, the same case? Technically speaking, yes, you may use this method, consistent partial least squares or PLSC, to estimate the same model with factors and components under this condition. This already I explained when I talk about PLS. So if your model is unidimensional and unidirectional and unconstrained, then you may use PLSC. Technically, yes, but in practice, this PLSC suffers very heavily from improper solutions, especially the PLSC uses bootstrapping to estimate the, again, standard errors or confidence intervals of the estimate. It's just simply disaster because almost always you have the improper solutions. So it's very hard to get the correct confidence intervals or standard errors in PLS. This is why I think, or to my knowledge, there's no software available for applying PLSC to estimate models with both factors and components. And that means, in practice, IGSA is the only option actually for estimating models with both factors and components. And personally, I believe having that kind of model with both factors and components can be more and more common in practice, as I said. So lastly, let me show one example about using IGSA based on this software. So in this example, we have 6 personality traits. And then we have 3 other actually constructs: job search, networking behavior, and number of job interviews, and the number of job offers. And the sample size is 773, some college graduates in northern areas of Vietnam. So here we have 6 personality traits from this very well-known the Sacco scale. And as I discussed earlier, the factors has been used to represent such psychological kind of personality traits. So just we use factors to represent these personality traits in this example. However, we use the components to represent the other constructs like networking behavior, the number of job interviews, and the number of job offers. Because as you can see here, these constructs items look quite sort of distinctive or heterogeneous. In other words, these items again kind of representing different aspects of the networking behavior, or as you can see, simply aggregating these two items will make this number of job interviews. Same thing here, just aggregating these two items will make number of job offers. We have a question in the circuit to measure component. Indicators. I'm not sure I'm following your question precisely. So, do you want to ask the researchers actually to specify, say, this construct will be a component or a factor in advance? I'm not sure that I'm following your question. Indicators have questions. Yes, please. Mm-hmm. So basically, each indicator, can be a question. Oh, so yeah, again, if I understand correctly, so actually these indicators are sort of questions in a survey, sure. And then if you think these indicators are kind of asking sort of a same thing in maybe different ways, then we may say, hey, there might be some underlying cause, which is, say, represented as a factor. Am I kind of following your question and answering smart PLS required question? The factor is here. I'm terribly sorry what this means. So factor is a question. Yeah, maybe this is sort of this is maybe the one way of the sort of representing a factor. So as long as this overall question is you think is a common cause of different say indicator questions, then this overall question might be considered as a factor. So I think whether this is question or not, that is not the kind of a real issue here. So as long as this overall thing, question or not, is the kind of common cause, making is indicators or smaller questions covariate, then you can just consider it as a factor. Okay. Okay, so again, so as I said, we have 6 personality traits represented as factors because they are all some psychological attribute. And then these 3 constructs represented as the components. So then, again, my computer is slow. It happens after I getting questions. Okay. Please be patient a little bit. Just a few more slides and okay, now it's moving forward. Okay, so then for this example, sure, as you can see now, we have these six factors or indicating different personality traits and that they are affecting networking behavior. And then this networking behavior in turn influences these two, the outcome components, the number of job offers and the number of job interviews. So let me run this model using, again, the software. Oops. Okay. So here again, so now, again, I'm going to create another new project for this IJSA case. So workshop, say test, say 3. This is a name for this new project. And I'm going to bring up the data file. So this is actually data file in Excel form again. Okay, now you have the new interface with all this data already uploaded here, as you can see here. So and then let me go back to this model tab. And then to run IGSA, it's always same place. You go here, analysis, and then just you choose the bottom one, IGSA, and then basic and single group. And then now in this left-hand side, now you have both components and factors at the same time. And as we discussed, we're going to use factors for these 6 personality traits. And then we have 3 components like this. And now simply you assign indicators to these factors and components. So the first personality trait is honesty, so H. So I can make this 10 indicators. And then next one is emotion, so E. And then this 10 indicators. Next one is extrovert, so X. These indicators. Agreeable. A. And then next one, conscientious. I'm going to call it C. Next one is openness. O. Okay, I'm done with the factor, the measurement model, and then the other components. Networking behavior. So these are the indicators for this component. And then this is a number of job interviews. So we have 2 indicators. And then last one is number of job offers. So bottom 2 indicators. Okay, then now we're done with the all measurement model part. And then just the same as before, just you add path coefficients, always from independent to dependent. So just need to add path coefficients. This. Okay, done. Then just same place, just you press this button, run. And this IGC has both factors and the components. And simply put, this is why it takes actually a bit more time than just running GSC or GSM. And this is timer showing the how many bootstrap samples are complete. So out of 100 now, it runs actually 27 samples and so forth. And right now, my computer is incredibly slow. But anyway, it's running. Please be patient. So 37 bootstrap samples complete, 43. Wow, it's really slow. $63. I don't know why it's so much time like this. Okay, so almost done now, 95 and 99. Okay, so it's done. Okay, thanks for your patience. And so this is not the case usually, but anyway, so now it shows all these modified measures again for this IGC, and then all these say estimate. For example, so these are actually the component, the loading estimate, because this networking behavior and number of job interviews and the number of job offers, they are components. So these are actually the component loading estimate, and all the others are factor loading estimates. And also these are path coefficients connecting the factors and the components or between components in this model. So sort of a same interpretations. So then you look at the statistical significance and also their size. Okay, so that's basically about it for this IGSA illustration. Okay, and just let me close this. And then just let me look at the questions. So okay, this is a bit the difficult actually the issue, but so far all I can say is so IGSA will produce unique actually the estimates of the loadings and all the other stuff, but not the unique actually the variables. And the sample size, it runs actually very well with the small samples. So sample size is not a big issue. But the thing is, it's just a common sense. If you have a small sample size, sure, your estimates will be less reliable. It happens to all actually statistical methods. So a larger sample size is better, but we don't have any kind of minimum sample size for the IGSA. Of course, you should have more actually the cases than number of variables at this point. But also to handle this kind of a high dimensional case, we now proposing the regularized IGCA, but this is sort of a new development which is not published yet. So in this software, so far, IGCA can handle the case of having more cases than the number of variables. But again, small samples. Oh yeah, I'll give you the references in following slides. No worries. Any other questions? Is it okay? Okay. So now we're almost done. Okay. I don't know why, but after getting these questions, and then the computer actually becomes quite slow. Okay, so this is the say a representative kind of a reference for GSCA for component-based SEM. So this is a book, and it explains all details, technical details, and the conceptual details of the GSCA, and also there are actually the sort of extensions. And then there are a bunch of different references published since 2015. And for IGSCA, so this one is actually talking about the Markov measures for IGSCA. And then actually this is the IGS paper published in the psychological method in 2021. So this is actually the main reference for IGSCA. And other actually the references. Again, I'd be happy to share all these slides with you guys. So just please let the Austin know about your interest about the slides. And then finally, this is the latest kind of a tutorial paper for this software just published this year. And this tutorial explains all these conceptual foundations of GSA SEM that I explained at this workshop, and also show the same actually the examples, and also explain all those the sort of steps of the running each illustration, and also the interpretation of the result. So I think this might be the first paper you may actually want to look at, and this is open access, so you can easily access this paper. So this might be my recommendation. Okay, so thank you. And do you have any other questions?
All right, then if there are no more questions, then let's all give a round of applause to Dr. Wang. Thank you so much for your presentation today. I think we've all learned a lot. And like you mentioned, if you want access to the slides or anything else regarding the presentation, just send me a message, and within the next day or so, the conference committee is going to send out the information to all the participants that are interested.
Okay, so great, and thank you, everyone, and okay, bye-bye.
Thank you so much.
Bye.